Hello everyone, my name is Yingchen. Today I'll talk about gpuzip on the side channel implication of hardware-based graphical data compression. This is a joint work with Ricardo, Zhao, Willie, David, Hava, and Chris. People have known for decades that compression can leak user secret because compressibility can be secret dependent. Let's see why with the famous crime attack from more than 10 years ago. The crime attack shows that an attacker with chosen input capability can learn secret cookies in secure network requests and responses. The reason is TLS compression compresses both attacker input and user secret together. If the attacker input happens to repeat partial user secret, the output network packet will be of smaller length. As a result, an attacker can brute force user secret by observing the length of the outcoming network packet from the victim. There are several more devastating attacks that abuse the similar compression side channel. However, here's a saving grace. Compression is typically software visible, and in this paper, we present gpuzip, a new type of compression side channel that challenges the conventional wisdom. The compression side channel we'll discuss inside this talk is first, software transparent, which means that the compression algorithm kicks in by itself without the software sending out any request. Second, the compression is microarchitecture specific and undocumented. This makes mitigation specifically hard because defenders cannot make any assumption about what compression algorithm will be in use. In this talk, I'll first introduce what is graphical data compression. We'll explain why it is different from traditional software compression, how it is involved in GPU-based rendering, and what we mean when we say it is software transparent and vendor specific. We'll also have a showcase of our tool. After that, we'll present our leakage model of graphical data compression and discuss that data-dependent microarchitecture traces the compression leave behind. Then we'll discuss the security implication of this compression by demonstrating an end-to-end attack. Finally, we'll discuss about mitigation. gpuzip explores graphical data compression, a feature that exists in almost all modern GPU nowadays. First, let's see why it is deployed everywhere. We live in a world where every single new generation of device must be shipped with higher screen resolution or higher screen refresh rate. In this figure, we use Google Pixel as an example, and we plot the maximum amount of pixel that must be transferred per second versus Google Pixel generation number. The trend is obvious. Indeed, DRAM technology is making progress simultaneously, but the increasing number of data that must be transferred on time due to GPU rendering can be a potential memory bottleneck. Do we really need to transfer every single pixel for the rendering to be accurate? If we want to render such a blue sky, we can observe that the sky is almost all blue with very little variances. As a result, almost all GPU vendors simultaneously chose a similar solution. Deploy graphical data compression directly into the GPU microarchitecture to improve data level parallelism and alleviates the potential memory bottleneck. However, graphical data compression is very different from any software compression we use every day. Most software compression we use, for example Deflate, aims to reduce memory usage. They do so by transforming the original data, like the 10 megabytes .bin file, into a more compact representation, like the 10 kilobyte .zip file. GPU graphical data compression, on the other hand, is kind of weird because it aims to solely reduce memory bandwidth usage with the cost of even higher memory usage. Let's see what they mean by looking at a concrete scheme, the graphical data compression used by Intel 8th generation integrated GPU. When rendering a surface, the GPU stores this surface by breaking it into tiles for better locality. The size of each tile is usually multiple of the physical page size. In this case, it is 4 kilobytes, 32 times 32 pixels. The GPU wants to get rid of the redundant information out of this tile, but it also wants to preserve the memory locality provided by tiling. So the GPU further breaks each tile into even smaller blocks and compress them individually. On this specific iGPU model, each smaller block has size of 2 cache lines and 4 times 8 pixels. The graphical compression applies to each of these blocks following a domain-specific compression algorithm that Intel invented themselves. The algorithm will look into each individual blocks and seek opportunities to compress it. If it can compress this block, it will compress the entire block from 2 cache lines into 1 cache line, and leave the other parts empty by just padding zeros. If it cannot compress this block, it will leave it as what it is. Now the question is, how does the GPU know which block it compressed and which one it did not? The answer is that it does not know. To save this information, it attached an auxiliary surface at the very end. The auxiliary surface allocates 2 bits to record down whether the data in a given block is the compressed representation or the original data. For example, the first 01 here means that the first block is compressed. When a GPU wants to read in its image with the help from the auxiliary surface, it only needs to read in the non-zero parts, and then it can perfectly or losslessly decompress the compressed representation to the original image. This is how GPU graphical data compression works. There exist many variants out there, but on a high level, all of them tries to transfer fewer number of bytes when creating the same visual effect by maintaining an auxiliary surface. Speaking another way, they try to reduce memory bandwidth usage at the cost of even higher memory usage. Now, let's see what we mean when we say this compression is software transparent by looking at how it is involved in a simple GPU-based rendering workload. Suppose a user wants to render such a gradient surface of 4 × 8 in total 32 pixels, the size of which is only 128 bytes, 2 cache lines, and 1 block. The smallest unit that compression will kick in. We expand each pixel to a bigger block for better visual effect. Every single pixel here has a designated color. We show the 2 cache lines of raw pixel data on the right-hand side, where the first cache line corresponds to the 4 × 4 group of pixels on the left-hand side, and the second cache line corresponds to the 4 × 4 group of pixels on the right-hand side. The user now writes OpenGL or Vulkan to render such a gradient surface. The backend implementation of OpenGL, very likely Mesa, will trap every single command from the user and talk to the kernel driver. Mesa will let the kernel driver know that the user wants to render such a surface with this specific size. Then the kernel driver will allocate 2 pieces of memory. If we zoom in to the first piece of memory at this moment, it contains the exact pixel we saw previously in row major format. If we look at the second piece of memory at this moment, it is empty. After all memory allocations are done, Mesa is notified, and then it tells the kernel driver that now it is the time to submit the job to the GPU to ask it actually do the rendering. The kernel driver will push the job to the GPU for processing. After the GPU finishes the job, we'll see that the piece of memory that is previously empty is not empty anymore. If we zoom into it, we'll find that the compression silently kicks in without the user making any request. And most importantly, the GPU identifies that the surface is compressible, so it compresses the original image into half of its size. And this piece of memory contains a compressed representation of the original image. Since the compression kicks in transparently by itself, every vendor is free to implement their own version. We constructed 4 different patterns shown in this slide: black, random, gradient, and skew. And we dump the compressed representation of them from 4 different platforms with integrated GPU from Intel and AMD. Inside this table, we present whether each surface is compressible on a given platform and put the compression ratio inside the parentheses. Indeed, the compression algorithm from different vendors are quite different. For example, AMD one is much more aggressive than that from Intel. Within Intel itself, the algorithm advances across generations. The fact that every single vendor implements their own version of compression algorithm without documentation is a big problem when we're trying to do security research on this topic. The reason is that when we're migrating across different platforms, the same pattern, for example, this one, ends up producing very different compressed representation. At one point, we start to wonder how sure are we that the compressed surface we see actually corresponds to the original surface. There's no easy way to confirm this, because all compression algorithms are vendor-specific and proprietary. Every company has their own version, and there's no public documentation. To confirm the compressed data we see actually corresponds to the original surface, we reverse engineered several proprietary graphical data compression algorithms. Here, I'm going to do a showcase of the tool that we built for doing reverse engineering, which we hope will make future research easier. The tool we built is called i915 tools. We provide three functionalities: dump, decode, and tweak. I'm going to showcase out the tweak functionality, which is also the most interesting one. The tweak functionality allows the user to extensively interact with the compression algorithm and efficiently launching a chosen ciphertext attack on the GPU graphical data compression. First, our tweak functionality allows the user to specify a surface they want to create using an efficient expression language. In this case, we're specifying that we want to create the gradient surface we saw throughout this talk. Then, it automatically finds the compressed surface that the GPU created by searching through the process address space, and allows the user to tweak pixels in the compressed surface. For example, we can say that tweak the highlighted pixel from 7F to 6F. After that, the tool will ask the GPU to decompress the tweaked compressed surface and provide the decompression result. In this case, we observe the decompressed surface has 1 byte deviated from the original one due to the tweaking we did. Tweaking the compressed surface is like launching a chosen ciphertext attack, where we treat the GPU compression algorithm as a black box, and by interacting with it, we learn information about its internal algorithm, gather linear equations, and finally reverse engineer. Inside our paper, we reverse engineer the compression algorithm used by Intel 8th generation and 11th generation integrated GPU, the underlying idea of which is prediction and residue. We also reverse engineer the delta color compression scheme used by AMD, which is way more complicated than that from Intel. If you're curious about more detail, please check out our paper and our codebase. Before studying the security implication of graphical data compression, let's look at the leakage model of graphical data compression. Suppose we prepare two surfaces that contain 6 secret pixels of different patterns, where pattern 1 is compressible and pattern 2 is non-compressible. What we observe is that because of graphical data compression, surfaces of different compressibility will leave ephemeral microarchitecture traces in the memory controller and permanent microarchitecture traces in the last level cache. A co-located attacker is capable of distinguishing pattern 1 from pattern 2. Now, let's see how an attacker can distinguish the two patterns by capturing the trace they leave behind in the memory controller. We set up a rendering experiment. Inside our experiment, we take a pattern and an integer iteration counter as input, and we ask the GPU to write to a big surface with this pattern and read that surface out, and keep doing this inside the loop. The goal of this experiment is to trigger the GPU to create memory traffic that heavily depends on the compressibility of the pattern being rendered. Indeed, when we monitor the DRAM read and write performance counter, we observe exactly half amount of traffic is transferred across the memory controller when the pattern is compressible. Since memory controller has a maximum bandwidth limit, less DRAM traffic would directly translate to a faster rendering time. That is what we observe as shown in the right-hand side of the figure, where the rendering time of the compressible pattern is smaller than that of the non-compressible one. As a result, a co-located attacker can easily distinguish which one is being rendered by measuring the screen rendering time. Similarly, a co-located attacker can distinguish the pattern being rendered by measuring the last level cache occupancy, the detail of which can be found in the paper. Now, let's move on to see the security implication of gpuzip. Traditionally, when we say secret, we mean secret key or password. However, secret can go way beyond this. When we're writing an email, everything rendered on the screen are user secret, including our current email draft or previous conversation with others. When we're entering credit card number, everything rendered on the screen is our secret. When we're browsing through a random web page that contains links to other web pages, every web page we have visited so far will be rendered to a different color. Those purple links are part of browsing history, and they are user secret. Every single graphical data rendered on our screen can potentially contain user secret, and GPU is the entity that handles everything we see on the screen. The fact that gpuzip leaks the compressibility of individual surface might not be too devastating, but there exists a concrete real-world scenario where a co-located JavaScript attacker in the browser can extract individual pixels by only learning the compressibility of the entire surface being rendered. The attack scenario is called pixel stealing. Pixel stealing attack is first introduced by Paul Stone in 2013 Black Hat. The attack violates the same origin policy on cross-origin iframes in the browser. We now introduce the standard framework to perform pixel stealing attack. Suppose we have a host web page which contains an iframe embedding a cross-origin web page. The same origin policy prohibits the host web page from accessing the cross-origin web page without obtaining its consent, because the cross-origin web page might contain private information. However, Chrome allows the host web page to perform almost arbitrary graphical operations on the cross-origin region with the SVG filter stack. By choosing proper SVG filters, the malicious host web page can cook up a specific filter stack to isolate, binarize, and expand a single cross-origin pixel to a big region of color white or black, then apply arbitrary graphical operations on top of the distinct patterns. Prior work shows that a malicious host web page can learn the content of the cross-origin one by rendering a SVG filter stack, because SVG filters used to be executed in the CPU and not implemented as constant time. Attacks from Paul Stone and Driscoll have shown how to launch such timing side-channel attacks. In response to the prior attacks, Chrome implemented their SVG filter in constant time and also offloaded the graphical operations to the GPU. The hope is that by doing so, the attack surface can be eliminated. What we show is that the attack surface is not eliminated due to graphical data compression. The attacker can construct the SVG filter stack such that if the target pixel is black after binarization, the SVG filter stack generates many black surfaces during the rendering. But if the target pixel is white after binarization, the SVG filter stack generates many turbulent surfaces during rendering. As a result, the SVG filter stack rendering time will be lower if the target pixel is black. The reason is that black surfaces are highly compressible, so the rendering triggers less DRAM traffic. Speaking another way, the malicious JavaScript attacker can extract the secret pixels in the cross-origin iframe one by one only by measuring the SVG filter stack rendering time. Inside our paper, we demonstrated an end-to-end user fingerprinting attack, during which attacker sends out phishing email with Wikipedia username sitting inside the iframe. The attacker's goal is to figure out the username, but they cannot see it due to the same origin policy. However, the attacker can apply a filter stack on it and then extract the username pixel by pixel by exploiting graphical data compression. The leftmost figure contains the raw Wikipedia username. The middle one is the same figure after binarization, and the right-hand side figure is the one malicious JavaScript attacker constructed using gpuzip. The attacker bypassed the same origin policy only by reading screen rendering time. gpuzip is yet another nice illustration of the missing hardware-software contract that is discussed heavily in the CPU microarchitecture security community. The real mitigation of gpuzip is for GPU vendors to provide a knob that software can use to easily disable compression when sensitive data is involved. However, this knob is not there yet. But people are putting in effort to bridge it together. A nice outcome of this paper is that it motivates the first software-oriented approach that tries to erase secret-dependent footprints in the GPU down to the microarchitecture layer. There is an ongoing Mesa patch that allows Mesa to create GPU textures with hardware compression disabled. However, this patch is only a workaround solution because there are cases where the hardware compression cannot be easily disabled, and the patch can impact software performance significantly. With that, I would like to conclude my talk. Inside this talk, we introduce a compression side channel that exploits GPU graphical data compression. different from all prior side channels that focus on software-visible and publicly known compression algorithms. GPU graphical data compression is software transparent and vendor-specific. We show this side channel is exploitable in the real world by demonstrating a pixel stealing attack. There exists an ongoing software mitigation, and we hope gpuzip can motivate GPU vendors to spell out the missing hardware-software contract in the future for better security isolation.